At 3:14 in the morning, a routine data packet landed on NASA's servers from nearly a million miles away. Within minutes, the public data feed for that one specific observation went dark. For 6 hours, nobody outside a small verification team said a single word about what the James Webb Space Telescope had just sent back. No press release, no statement, just silence from an agency that, more than almost any other, has built its entire public reputation on sharing everything immediately in stunning color. Here's what Webb actually saw, why it triggered a quiet communications blackout, and why the real explanation is stranger than the silence itself. To understand why 6 hours of silence is actually a big deal, you first need to understand how James Webb normally operates day to day. Unlike a lot of NASA missions from earlier decades, Webb's raw data doesn't sit locked away in some private vault for years before anyone outside the mission team gets to see it. Within a set proprietary period, the vast majority of it becomes fully public, uploaded to an open archive anyone with an internet connection can search. Scientists comb through that archive constantly. So do journalists. So do a growing community of amateur astronomers who have gotten remarkably good at spotting interesting signals in raw data long before any official announcement goes out. That openness isn't an accident. It's by design, part of a deliberate strategy that helped Webb build its public reputation, not just as a discovery machine, but as one the entire world got to watch unfold in something close to real time. Which is exactly why a sudden, unannounced pause in one very specific data stream immediately stood out to the small community of people who watched that archive closely, day in and day out. The observation in question wasn't of some spectacular glowing nebula or a distant galaxy cluster, the kind of image that ends up on magazine covers. It was something far more specific and far less flashy on the surface. A scheduled spectroscopy reading of a single exoplanet's atmosphere, a routine follow-up observation on a world astronomers have quietly been tracking for years. Routine, right up until the moment it wasn't. Here's how this particular kind of observation normally works, and why it's so different from simply pointing a camera at something far away. Webb doesn't take a photograph of an exoplanet the way you'd naturally picture a photo, with a clear, recognizable shape sitting against a black background. Instead, it watches starlight pass directly through that planet's thin atmosphere during a transit, as the planet crosses in front of its host star from Webb's point of view. As that starlight filters through the atmosphere, Webb breaks it apart into a full spectrum, essentially a detailed chemical fingerprint hidden inside ordinary light. Different molecules absorb very specific, very narrow wavelengths of that light as it passes through. Read the tiny gaps in the resulting spectrum correctly, you can determine, with real confidence, what's actually floating in an alien atmosphere millions of miles away, without ever sending a single physical probe anywhere near it. It's one of the single most powerful tools in all of modern astronomy. It's also one of the most heavily scrutinized, precisely because the margin for error in reading these signals correctly is genuinely razor thin. This time, the spectrum that came back from the telescope contained an absorption signature that simply didn't match the expected model. Not a small, easily dismissed deviation either. A distinct, unmistakable dip at a wavelength strongly associated with a specific class of sulfur-based molecules, the exact kind most commonly produced by biological processes here on Earth. That single word, biological, is precisely why 6 hours of careful silence makes complete sense once you understand the full context. It's also exactly why nobody on that team wanted to say anything publicly before they were absolutely certain of what they were looking at, because this isn't actually the first time a sulfur-based signal like this has shown up in an exoplanet's spectrum and caused a stir behind the scenes. A strikingly similar signature made global headlines a few years earlier, tied to a completely different world, and the fallout from that earlier announcement taught every team involved in this kind of research a hard, memorable lesson about the real danger of moving too quickly. It's worth stepping back for a moment to understand exactly what kind of machine produced this signal in the first place, because that context matters. James Webb launched on Christmas morning several years ago, folded up like origami inside a rocket fairing, only to unfold itself piece by piece over the following weeks, nearly a million miles from Earth, far beyond any possibility of a repair mission if something went wrong. It carries several distinct instruments, but the one responsible for this particular observation is a spectrograph purpose-built to split incoming starlight into extraordinarily fine detail, sensitive enough to detect the faint chemical fingerprint of an atmosphere on a planet that never appears as more than a single point of light, even through Webb's own massive mirror. That instrument has already made history once before, on a different planet entirely, one that's been at the center of exactly this kind of debate for years now. A sub-Neptune world orbiting a small, cool star roughly 100 light-years away first grabbed headlines when Webb detected hints of a similar sulfur-based molecule in its atmosphere, alongside signs of methane and carbon dioxide that suggested a genuinely unusual atmospheric chemistry. That earlier announcement was handled carefully from the very beginning, hedged with statistical caveats and repeated statements that more data was needed before anyone could draw firm conclusions. Even so, it still ended up on the front page of major news outlets around the world, framed by some as the strongest biosignature candidate ever found, and criticized by other scientists as a statistically weak signal getting far more attention than the data actually supported. That earlier case is the direct ancestor of the caution playing out here. The team behind this newest signal watched that entire debate unfold in real time, watched how quickly a hedged, careful statement got flattened into a much bolder headline once it left their hands, and adjusted their own process accordingly. Here's the uncomfortable truth sitting at the center of a signal like this one. The specific molecule in question absolutely can be produced by living organisms, but it can also, under a very particular set of atmospheric conditions, be produced by nothing living at all, outgassing from an unusual ocean chemistry driven by volcanic activity or triggered by photochemical reactions we still don't fully understand yet on worlds this different from our own. Which means the single most exciting possible explanation sitting on the table is also, statistically speaking, one of the least likely ones to actually turn out to be true. The team that first received this data understood that immediately, without needing anyone to explain it to them. And they also understood, in vivid detail, exactly what happens once even a small hint of a possible biosignature leaks out before it's been checked 6 different ways from 6 different angles. So instead of releasing the raw data on the usual automatic schedule, they made the deliberate choice to pause it. They quietly pulled in a second fully independent team to reprocess that exact same narrow wavelength range from scratch, using entirely different calibration methods, specifically designed to rule out any kind of instrument artifact. A stray internal reflection inside the optics, a subtle calibration drift building up over time, a cosmic ray striking the detector at exactly the wrong possible moment during the exposure. Any one of these could, in theory, mimic a real signal that isn't actually there. 6 hours doesn't sound like a particularly long stretch of time in the grand scheme of things, but for a telescope that transmits data almost continuously around the clock, deliberately holding back one specific stream while everything else kept flowing normally out to the public was itself a signal. It quietly told the handful of people paying close attention that something inside that particular observation needed a careful second look before the wider public ever laid eyes on it. And that's the part almost nobody outside that small, attentive group actually noticed in the moment. It wasn't a system failure. It wasn't some embarrassing malfunction being quietly covered up. It was a choice made under real pressure by people who understood exactly how much weight a single word like biosignature can end up carrying once it's loose in the world and impossible to fully take back. When the second team's independent reanalysis finally came back, the signal was still there. Weaker than it had appeared on the very first pass through the data, but genuinely present, sitting in almost exactly the same narrow spot in the spectrum as before. That single result ruled out the simplest, most comforting explanation available. A one-off detector glitch that would have quietly explained everything away in a matter of minutes. But it didn't rule out everything else, still sitting on the table. The team methodically cross-checked the finding against the planet's known temperature, its best current estimate of atmospheric pressure, and existing models of exactly what kind of non-biological chemistry could plausibly produce a signal like this at that specific depth in the atmosphere. 2 explanations managed to survive that entire filtering process intact. 1, an unusual, previously theoretical photochemical reaction driven by intense radiation from the planet's host star, something scientists had discussed on paper for years but never directly observed in practice. 2, the far more sensational possibility that the sulfur signature genuinely does trace back to some form of biological activity. Neither explanation could be confidently ruled out using only the data currently in hand. And that, more than any single other factor, is exactly why the silence stretched out to a full 6 hours, instead of quietly ending in 20 minutes with a simple internal note reading instrument error, please disregard. When the data finally did go fully public, it went out attached to an unusually long, detailed technical note. Page after page of careful caveats, alternative explanations, and a clear, deliberately worded statement making one thing explicit. This finding does not confirm life anywhere, only an unexplained signal that genuinely deserves more dedicated observation time. That's a very different tone from most of what actually ends up making headlines in this field. And it's exactly the tone you'd expect from a team that had just spent 6 full hours making absolutely certain they weren't about to overpromise something they couldn't fully back up with hard evidence. It's worth remembering that this caution didn't come out of nowhere. The entire field of exoplanet biosignature research has been shaped, quietly but permanently, by a handful of earlier moments that didn't go nearly this smoothly. A few years before Webb ever launched, a completely different research group announced a possible detection of a similar molecule in the thick clouds of Venus, our own uncomfortably close planetary neighbor. That announcement moved through the news cycle at incredible speed. Within days, it wasn't being framed as a cautious, tentative result anymore. It was being framed, across countless headlines, as evidence that life might exist in the clouds of Venus itself. Follow-up studies, conducted over the following months and years, repeatedly failed to confirm the original signal at anywhere near the strength first reported. Some newer analyses questioned whether it had ever really been there at all in a statistically meaningful way. The damage from that entire episode wasn't really scientific in the end. The underlying question about Venus's clouds remains genuinely open and still worth studying carefully. The real damage was to public trust, and to how quickly outside observers assumed the very next similar claim would also collapse under closer scrutiny. Every team working in this exact corner of astronomy since then has operated with that specific memory sitting quietly in the back of their minds. Move too fast, and you risk becoming the next cautionary headline instead of the team that got it right. Which brings us back to that unusually long, careful pause. 6 hours of silence wasn't the system failing to communicate quickly enough with the public. It was the direct, lived result of an entire field having learned, the hard way, exactly what happens when caution gets skipped in the rush to say something exciting first. The planet at the center of all of this is now scheduled for a fresh round of additional observation time later this year, using a different instrument mode specifically designed to nail down that exact wavelength range with far more precision than the original scan ever could. If the signal genuinely holds up under that more sensitive, more targeted follow-up, it still won't be a confirmed discovery of life anywhere. It will be something narrower in scope, and in its own quiet way, arguably more interesting. It would mark the first time a major space telescope caught a genuinely ambiguous biosignature candidate, handled it with visible, documented caution from the very first hour, and showed its work openly and close to real time instead of rushing straight to a triumphant headline. If the follow-up observation doesn't hold up, that's not really a failure either, whatever the more sensational corners of the internet might eventually claim about it. It's exactly how this kind of careful science is supposed to work in practice. Chase the signal wherever it leads, check it from every conceivable angle available, and ultimately let the data decide the outcome, even when the far more exciting answer is the one almost everybody secretly wants to turn out to be true. It's worth asking, too, what a confirmed result like this would actually change, beyond a single dramatic headline. For decades, the search for life beyond Earth largely meant scanning the sky for deliberate radio signals, listening for something that looked unmistakably artificial, sent our way on purpose by another intelligent civilization. Modern biosignature science works completely differently. It isn't looking for a message. It's looking for the accidental chemical exhaust of ordinary biology, the same way Earth's own atmosphere is thick with oxygen and methane sitting together in a combination that shouldn't persist naturally for very long without something alive constantly replenishing it. If a similar chemical fingerprint ever gets confirmed with high confidence on a world light years away, it wouldn't prove intelligent life exists out there. It would suggest something arguably even bigger in scope, that biology itself, in some form, might not be a rare accident confined to a single planet, but a natural outcome that happens wherever the right conditions line up. That's an enormous claim to rest on a single spectral line, which is exactly why every team encountering a signal like this treats it the way you'd treat a smoke alarm going off in an empty house. Worth taking seriously immediately, but not worth calling it a fire until someone has actually gone and checked the kitchen. There's a broader pattern hiding underneath this one specific story, and it's worth sitting with for a moment before we wrap up. Every single time Webb has produced a genuinely ambiguous, borderline result like this one, the actual scientific process behind the scenes has looked remarkably similar. Pause, verify independently, cross-check thoroughly against every known alternative explanation. Only then, finally, communicate clearly and honestly with the wider public. It's slower than the modern news cycle would obviously prefer. It's also almost certainly the only responsible way to handle a topic this significant, given the sheer size of the claim potentially sitting on the other end of it. Because if a real biosignature candidate is ever confirmed on some distant world, it won't just be a single exciting headline that fades within a week or two. It will permanently reshape how an entire generation thinks about our own place in the universe, and about the odds that we are genuinely alone out here. That kind of claim deserves exactly the kind of careful scrutiny this specific signal quietly received, 6 hours at a time, largely out of public view. 6 hours of silence from one of the most transparent missions in NASA's entire history wasn't a mistake, and it wasn't something being deliberately hidden away from the public. 6 hours of silence from one of the most transparent missions in NASA's entire history wasn't a mistake, and it wasn't something being deliberately hidden away from the public. Think for a moment about the actual people sitting in that verification room during those 6 hours, because it's easy to talk about the team as an abstraction and forget there were real individuals making real decisions under real pressure. Some of them had almost certainly been part of the earlier debates over that other sub-Neptune world, watching a hedged, careful announcement spiral into something far bolder than they ever intended once it reached the public. Some of them likely remembered the Venus cloud controversy even more vividly, having watched colleagues spend years quietly trying to walk back a claim that had already become fixed in the public imagination within days of the original headline. Sitting with a fresh, unexplained sulfur signature at 3 a.m, that history wasn't some abstract lesson from a textbook. It was a lived memory shaping every decision they made in real time, hour by hour, as the reprocessed data slowly came back in. There's a particular kind of pressure that comes with being the person who has to decide whether to hit send on a data release that could plausibly become the biggest science story of the decade, or plausibly turn out to be nothing more than an artifact of a slightly miscalibrated detector. Both outcomes carry real consequences. Move too fast, and you risk becoming the next cautionary headline, the next case study future scientists cite as a warning about premature announcements. Move too slowly or too quietly, and you risk being accused of hiding something from a public that funded the mission in the first place. The 6-hour window sits right in the middle of those two competing risks, and in hindsight, it looks like a fairly reasonable compromise. Long enough to genuinely rule out the most obvious, most embarrassing possible errors. Short enough that it never crossed into anything resembling a cover-up. It's also worth remembering that this entire process happened without a single leak, without a single premature tweet from inside the team, at a moment when a single screenshot could have ended any chance of a careful, controlled release. That kind of discipline doesn't happen by accident. It reflects a team culture built specifically around the understanding that a claim this significant only gets one real first impression with the public, and that impression is almost impossible to fully correct once it's out in the wild. It was restraint. A small, focused team choosing to double-check a genuinely extraordinary possibility before letting the rest of the world see it, precisely because they understood exactly how easily a single unexplained data point can spiral into a headline nobody can fully walk back afterward. That kind of caution doesn't always make for the most satisfying possible answer, especially not in the moment, but it's exactly what separates a real, durable scientific finding from a rumor that spreads faster than anyone involved can ever hope to correct. Every additional hour of verification behind the scenes is, in its own quiet way, a form of respect for how much this specific question actually matters to people. It would have been easy to release the raw numbers immediately, let speculation run wild across social media, and deal with the consequences afterward. Instead, the team chose the harder, slower path, and stood behind it, even knowing some people would read the delay itself as suspicious. That choice says something meaningful about how the most consequential science tends to actually get done. Away from cameras, away from headlines, in quiet rooms full of people cross-checking each other's work before anyone else is allowed to see it. It also says something about what the next few years of this particular field are likely to look like. Webb wasn't built to answer this question once and then move on. It was built to keep watching, keep collecting spectra, keep narrowing the odds a little further with every additional transit it manages to capture. The follow-up observation scheduled for later this year is really just one data point in a much longer campaign, one that will likely stretch across many more transits of this same distant world before anyone feels confident calling the question settled either way. That's a strange kind of patience to ask of a public used to instant answers, delivered the same day, wrapped in a single dramatic headline. But it's the only version of this process that actually respects how enormous the underlying question really is. Somewhere out there, on a world we'll likely never visit in person, in an atmosphere we can only study by watching starlight pass through it from nearly 1 million miles away, a very small, very ordinary-looking chemical signature is quietly forcing some of the most careful scientists in the world to double, triple, and quadruple check their own work before they'll let themselves believe it. That, in the end, might be the most reassuring part of this entire story. Not the signal itself, and not even whatever it eventually turns out to mean, but the fact that the people trusted with finding it are still willing to sit with genuine uncertainty for 6 long hours, rather than hand the world a headline they aren't fully sure they can stand behind. If you want to know what that follow-up observation actually finds, and whether this exact signal survives a second, far more precise look later this year, that's exactly what I'll be covering the moment the new data lands. Subscribe so you don't miss it when that follow-up finally goes public. And before you go, tell me in the comments, if you had to bet right now, knowing everything you just learned, do you think this particular signal eventually turns out to be biology? Or some strange chemistry we simply don't understand yet? I'll be reading through the answers, and I'll pin the one I think makes the most convincing case.